Good morning, everybody. Let's get started. Welcome to today's installment of our lecture on image processing, retrieval and analysis. Here is what we will be discussing today. Actually, today is rather a recap day. We'll have another look at what we have been doing last time, more or less extensively. And then I have to tell you about some other elementary ideas. And we will end today's lecture with reconsidering what we have been doing so far and looking at why we have been doing this. Because, as we will see, all of what we have been doing so far will prepare us to shift gears now, to I don't know, accelerate and to do something rather interesting and probably not so well known the next couple of lectures. But let's see how this goes. The major reason for all our discussions in the last couple of lectures or weeks is that in the very end, towards the end of this semester, we want to understand how to transform this into something like that. And we have already talked about how we can think of images and that they may be functions and that we may do something to the coordinate space, to the domain over which the function is defined, in order to create certain effects. In particular, in the last lecture, we discussed affine transformations. Remember that we can, our starting point was that we assumed that this two-dimensional plane is the domain over which an intensity function is defined. All of this would also hold for color images, but it's easier to talk about intensity images, and we can immediately apply this to color images if we want. All right, now we said that this two-dimensional plane is the domain over which an image function is defined, and then we looked into ways of, I don't know, transforming the coordinates, points in this plane. And a very important special case is the idea of rotations. And actually we went through this in quite some detail, but remember that we said, well, if we are given a certain point P in a certain coordinate system, which we assume to be Cartesian, that is to say, this coordinate system, the blue one, is defined by two unit vectors, u hat and v hat, and they are orthogonal to each other. And in terms of linear algebra, we could say these two vectors, u and v, span this two-dimensional space. Now, with respect to the axes u and v, this point P has a coordinate of pu along this direction and a coordinate of pv along this direction. Then if we assume that there was another coordinate system which, say, has the same origin than the blue one, but is somehow rotated away from the blue one by an angle of phi. And again, we require unit vectors, if we're talking about Cartesian systems, that would determine this coordinate system. Let's call them x hat and y hat. Then with respect to this system, the point P has different coordinates. Right? All we have to do is to compute the orthogonal projection of this point P onto the x-axis and onto the y-axis, and we find that with respect to the vectors x hat and y hat, P has coordinates px and py. And the conceptually important thing here is that if we look at that picture, it tells us that if we're talking about transformations, we can either think of it as doing something to the point or doing something to the coordinates. to the coordinate systems. Sort of like either we change the point or we change our point of view. And at the end of last lectures I said that as a student I preferred the point of view of we do something to the point, and now for a couple of years I prefer the point of view that we change our perspective. In this example that would basically mean we rotate our heads. If we accept the idea that we can understand this picture as the point remains the same, I'm not moving this point around, the point remains the same, but depending on our point of view, our perspective, which is to say depending on our coordinate system, it can express in different ways. And what we studied last time was the question how to translate the PU-PV coordinate of the point expressed in the UV system into the PX-PY coordinates of the point expressed in the XY system. And after some straightforward algebra, we found that this can be expressed like that. So if we assume the point to be a vector, we can express the point as a two-dimensional real-valued vector with elements PU and PV. And we can assume the point in the XY coordinate system to be a two-dimensional vector with elements Px, Py. And we derived this matrix as the transformation that takes the vector in its PU-PV coordinates into the vector in its Px-Py coordinates. Yeah, and a shorter way of writing this is to assign names to these three objects here. Say this would be the vector PUV, this would be the vector PXY, and this matrix would be the matrix R phi, where the subscript phi indicates that we assume this angle by which the one system is rotated away from the other. We assume it to be given. And this is still too much effort to write down every time. So from now on, I will refer to this situation by means of this equation. Right? And this sort of implicitly means that we are talking about a point P in a UV system, and so I'm not calling it P anymore, but U. And we're talking about a point, the same point in XY system, and I will refer to this point in the XY expression as X. And the matrix is just called R, where we implicitly assume that R depends on some angle phi. And then we briefly looked into the problem, now that we know how to transit from the UV system to the XY system, how to go back. Right? And with respect to two-dimensional rotations, we know, if we go from one system to the other just by tilting our head this way, well, then the back transformation would be this. So rotations can be easily inverted. And this is because of these properties. We ever so briefly discussed that the matrix R we uncovered on the previous slide, or derived on the previous slide, has certain very special properties. It is a square. In our case here, it's a 2x2 matrix. It has a determinant that is exactly 1. Its two columns, let's call them C1 and C2, are orthonormal vectors. That is, both columns, the two columns, are orthogonal to each other. This is the ortho in the orthonormal, and in addition, this is a vector of length 1, and this is a vector of length 1. This is the normal in the orthonormal. So the columns are orthonormal, perpendicular to each other, and both of them are of length 1. The same applies to the rows. Let's call them R1 and R2 in this case. They are also orthonormal. And yeah, because it's a rotation, the back transformation is just transposing the matrix. And I said, be very careful. Do not assume that this is just because it appears on this slide that the inverse of a matrix equals the transpose. This is of course not true in general, but for rotation matrices it is. And all of this is to say that the matrix R we are talking about is a member of a very exclusive club. And that club is called the group of the special orthogonal group defined over the 2 by 2 dimensional matrices over the real numbers. And ever so briefly, I motivated why we use this notation here. And I will use it possibly quite frequently later on in this lecture. And okay, so to really wrap this up, if we say that the back transformation is just the transpose of the matrix, well then of course we just have to transpose the matrix, right? And this is to say the minus sign flips from here to there, it's just a transpose. Well, in the last lecture we actually looked at all the affine transformations there are. I had a list, and actually the list was comprehensive. There are no other affine transformations, elementary affine transformations, in addition to the ones we discussed. And I said that not just the rotation we discussed can be expressed in terms of a matrix vector operation, but several others, not all of them, this is important, several others of the affine transformations can also be expressed in terms of matrix operations. And of course, any composition of a couple of affine transformations, that is say if we apply a couple of different affine transformations successively, that is indeed as if we were to apply a more general affine transformation. So if we apply them in succession, it's another affine transformation. And if these affine transformations, which we apply in succession, can be expressed in terms of matrices, then of course we could probably construct a matrix that would represent this more general affine transformation. And indeed we can. We would just have to multiply these individual matrices together in the order in which we want to apply them. This is important because matrix multiplication is in general not commutative. And we looked at this example where there is an image given, a function g, defined with respect to some coordinates. Then if we do something to the coordinates, say, well, okay, so now I'm actually talking about let's do something to the coordinates. We can sort of change our point of view. It's really the same thing. But if we apply a rotation to the coordinates over which the function is defined, then we obtain a new function. Let's call it g tilde. And if we apply another affine transformation, say the idea of shearing this function or the coordinate vectors along the x-axis, we would obtain this function. I probably should have given it different names here. This is not very smart on my part. But you know that even though both of them are called g tilde, it's actually not the same thing, right? Sorry about that, but the take-home message of this slide is, now if we were to compose these two transformations into a single one, it makes a difference if we first were to rotate and then to shear, we would get this, or if we first were to shear and then to rotate, in that case we would get that. And these two images as we see them here are obviously not the same thing, and this is really to hammer it home that the product S times R is in general not the same as the product of R times S. Of course, we can choose the components of these matrices such that it indeed would commute. Right? For instance, if R was the identity matrix, very boring rotation, it doesn't do anything, but it's a rotation matrix. Right? In that case, it would commute, but in general, it does not. And then Well, now that we had talked about linear transformations, matrix multiplications, well, to me it's the same thing, you see. Now that we talked about matrix multiplications, we looked into the idea of what it means for a transformation to be linear. And I said that if something can be realized by means of a matrix vector multiplication, that something is a linear transformation. And a linear transformation, let's very generally refer to it as T, is called, or such a transformation is called linear if it obeys these two properties. Quite frequently in textbooks you actually find these two equations meshed together in just one equation. This is easy to do. We could have this alpha here and in front of this sum, and you could have just one equation. I prefer this two. It's just to point it out more emphatically. Right? But if we're given two objects, let's call them u and v, and for the sake of the argument, let's say they are vectors. Does not necessarily have to be vectors, but if they are vectors, because right now we're talking about vectors, and we apply the transformation to the sum of u and v, then this has to be the same as if we were to transform u and transform v separately and add that together, and at the same time, if we were to transform a scaled version of u, this has to be the same as if we were to scale the transformation of u. If this is given, the transformation is called linear. Linear transformations are a staple of all of science. It's not just in image processing. You will certainly have seen them before. This is because if something is linear, it is really easy to manipulate. I'm just saying. However, in the context we are dealing with right now, affine transformations, we have to remind ourselves that not every affine transformation is linear. In particular, if we look at the affine transformation of translating something, so we're given something and we sort of shift it around, is affine. It preserves certain properties, which we will come back much later to. Shifting something around is an affine transformation, but if this something lives in a two-dimensional space, we cannot express this operation of shifting it around in terms of a matrix vector multiplication. And therefore, in general, an affine transformation consists of two parts. There is this, in 2D, idea of some linear transformation, like we can rotate, shear, scale, all these things can be done in terms of a matrix vector multiplication. And if we at the same time also want to make sure that this translation is not lost, we would then have to add another vector to that. If we express this equation in a shorter form, again we have these vectors u and t as we had earlier on, we would now say that if we're given, say, a coordinate vector u and want to produce a new coordinate vector x, in general an affine transformation in the 2D plane would be to multiply a 2x2 matrix to u and add some translation vector. And really, this is important and dear to my heart that you accept this. Because I typically ask that question in the exam, and this shouldn't be something where you go wrong. All right? Every linear transformation is affine, but not vice versa. Okay, and at the very end of last lectures, where we looked into some simple exercises you could do at home, I asked the question, can you conceive of a way of turning this generally nonlinear transformation into a linear operation? And it turns out that can be done. And to this end, we have to borrow ideas from a field that is called projective geometry. And those of you who are attending the computer graphics courses will have seen that before. I will not at all dive into what it is that makes a geometry projective. Very interesting topic, but I would hope that this is discussed in computer graphics. So just accept the fact that this term appears on this slide, but we can nevertheless, at least intuitively, understand the idea. And the idea is to embed n-dimensional vectors in an n+1 dimensional space. In our case, so far, the vectors we have been interested in were these two-dimensional vectors, and so therefore if we want to embed n equals two-dimensional things into something n+1 dimensional, in our case, that would be three-dimensional. And here we go. This is the conceptual step we can take. We are given a vector xy, and we may mentally think of this vector as there's a one-to-one correspondence between this two and this three-dimensional one. If we do it like this, we choose some number w, ideally different from 0. Actually, it has to be different from 0. And we transform this into that. Basically by multiplying the first coordinate x with w, multiplying the second coordinate y, w, and adding a third dimension, which is just this number w. And really, like typically, this number w is chosen to be 1. So what we are interested in right now is vectors, two-dimensional vectors, which we express like this. It is now a three-dimensional vector, but let's have a look at how we can think of this. Now, on the left-hand side, we see the coordinate plane that has been in the focus of our attention for the last couple of lectures. And I have, I don't know, indicated a certain point in this plane. And now, if we were to think of this plane as being a plane, let me create a plane here, a plane, two-dimensional plane that lives in 3 dimensions, right? And we have not specified a coordinate system for the 3-dimensional space, then we can always say, and this is just to our liking, that this is indeed a plane in 3D which happens to live at x coordinate 1, if we choose this w to be 1. Right? But in general, it happens to live at x coordinate w. And this is to say, the point that has a certain x and a certain y coordinate in this two-dimensional representation now has the same x and y coordinate, but we somehow lift it to another, somewhere above the xy plane. This is a way of thinking about this, and it is just a metaphor, because this is not how people in projective geometry would think about this, but for our purposes this is good enough. Why would we want to be interested in something like that? Because if we apply this trick, then we can indeed express translations of two-dimensional vectors in terms of matrix multiplications. Right? We just have to. This is again raising the level of abstraction. But if we do that, and we compute x plus a, y plus b, 1 plus 0, to get x plus a, y plus b, 1, this is indeed now expressible in terms of this matrix, where along the main diagonal we have lots of 1s, and then we have an a and a b in this third column. And this third column did not exist when we were talking about two-dimensional matrices, but now we have it, and you can easily verify that if we multiply this matrix to that vector, we get actually actually this vector. Do we really need that? Is that something we want to, I don't know, like really want to worry about? No, it's not necessary, right? Because we can, of course, if we want to compute affine transformation, always do it like this. The only reason why I am talking about this is that this is commonly done this way in practice, because if you are to implement software that does all this for you, if you were to implement it over two-dimensional vectors, you would have to worry about a function that does matrix multiplication and a function that does vector addition. And in this representation, all you need is a library or software that does matrix multiplication. Right? That's basically all there is to it. And in particular, in computer graphics, that comes in very, very handy, because they basically do nothing but this. I'm very careful now, because if somebody with a background in graphics would watch this video, sorry about my bluntness here. Now, and one way of sort of turning this equation we have seen previously into this homogeneous representation is basically to say that we are now talking about the three-dimensional vectors, where this first component actually is a two-dimensional vector, third one is 1, and then we have a 3×3 matrix where the 2×2 matrix in the upper left corner is the matrix M, and we have a vector T in this first two rows of the third column. Here is the translation vector T. The last row is given by 2 zeros, as we see there, and 1. That is all there is to it. And the reason I am discussing is that we can, it's, you know, it sort of simplifies our notation. Right? It's like, it's a, if we were to study it in all the detail there is to it, it would be a very huge conceptual step, but we ignore all these specificities here. We are just interested in that so that I can, you know, write down affine transformation in a more simple manner. For instance, the rotation we have been talking about would become this expression. There's not a lot to it. And this matrix rotates the image about the origin. And so the question is, what could we do if we wanted to rotate a given image about a point different from the origin? How could we do that? Well, with what we just learned, actually with what we learned earlier, we would apply this algorithm. We first would have to change our point of view, and that is to say, we would express the point about which we want to rotate the image, say not the origin, but some other point. We first would apply a transformation that transforms this point P to the origin of a corresponding coordinate system. First do this. In that new system, we would then rotate about the origin. Now we would get a corresponding representation of the image, which we then would have to transform back to the original, so that the original origin is given again. And we can express these three steps by means of one expression here. But this is the original vector we are given, and we want to rotate it about a point AB. We express this in terms of this minus. First we move this point such that AB becomes the origin of the system we're talking about in the first step. We can do this by multiplying this matrix to this vector. Next is we rotate. Now we just rotate about the new origin. That is, we just use the matrix we have been deriving earlier on. Once this is done, we apply this third transformation, which transforms back to the original origin. A picture says 1,000 words. Here we go. Right? So this is the image. This is what would happen if we were to rotate it by an angle of 12 degrees about the origin. And apparently, in this example, the origin was up here. This is sort of the matrix representation of that image, where I said if we're talking about images as matrices, the origin is this point. Yeah, well, I apparently use the origin as the point up here. If I rotate this image about this point by 12 degrees, then this is what we get. Note again that there are, if we were to create a new image that has exactly the same size as the original one, then there are certain areas in this new image for which we don't know what color to set there, because it's not contained in this image. I just set it to black. If we were to rotate the image about the origin, which is to say about this point here, well then, of course, our brains immediately recognize, yeah, this is a rotation about this point here. But in order to do this, I really applied these three matrices we see here. Ever so briefly, let's talk about efficiency and how this would be done in practice. And let's discuss it by means of this example. This is the transformation we want to apply. We want to rotate something about a point AB, and we just discussed that this equation does the trick. How would we implement this on a computer? Right? This is indeed actually probably overkill what we're discussing right now, but I am just discussing it to point out that there is a difference between mathematics and implementation of mathematics on digital computers. Right? Because from the mathematical point of view, everything we need to know is actually here. And now we want to do it in practice. How do we do that? And by asking the question, how do we do that? What I am referring to is that we can do this, for instance, by multiplying this matrix to this one, multiplying the result to this matrix, multiplying the result to the vector. We could also multiply this matrix to the vector, then multiply this matrix to this vector, then multiply this matrix to this vector. It's different, right? It's actually very different because if we multiply two n by n matrices, as we are given here, n is 3 now, 3 columns, 3 rows. This is an operation that is of the complexity n raised to the third. Okay? Because let's ever so briefly think of it. We have to compute the, let's look at the product of this one and this one, to compute the first element. If we want to multiply these two matrices, that gives a new 3 by 3 matrix. Right? And in order to compute the 1, 1 element of this new matrix, we would have to compute the inner product between this row and this column here. Right? And this requires 3 operations of multiplications and corresponding additions. 3. Right? But we only did this to compute the first element of this new matrix, but there are 9 elements. So n square elements times n operations. This is why, in general, matrix multiplication is of the order of n to the third. There are very, very clever ways of reducing the complexity of matrix multiplication. And this is indeed extremely important in practice because a 3 by 3 matrix is good and well, but if we were to do weather forecasting, which involves solving lots of systems of linear equations and differential equations, we're talking about matrices where this n is in the order of millions. And millions cubed is something that is very expensive. And so people have been looking into what can we do it more efficiently. And there are extremely clever ways of doing it more efficiently by rearranging these matrices and so on and so forth. We will not go to look into that. Strassen was the first who did it, actually pushed it down from 3 to 2.807 about, which does not look like much, but if this n is a billion, then this is a lot, right? And right now the state of the art is, I guess, at somewhere 2.3 something. So that, I said, naive is of the order n to the third. If you use state-of-the-art libraries for numeric computing, your software will not do it like this, but rather use these algorithms. And at the same time, matrix vector multiplication just requires n-square operations. Why is that? If we look at the product of this matrix and this vector, and we would obtain another vector if we multiply it, to compute the first element of this new vector, we just have to compute the inner product of the first row and this vector. Right? But we have to do it 3 times. Right? So therefore this is just n squared. But that is to say that if, in this example, we were to multiply this to this and this to the result, we would have to compute 2 matrix-matrix multiplications, in our case 2 times 3 to the third, and 1 matrix vector multiplication. We would have to have operations in the order of 63 here with this tiny simple example. But if we were to multiply the one matrix to the vector, then the next matrix to the resulting vector, and the next matrix to the resulting vector, we would only have to carry out 27 operations. Interesting, right? So I'm just saying, if you are faced with the problem of putting mathematics into computer code, think about what you are doing. You don't have to, but then you have to wait. Okay? It's a great occasion for us to just point out these practical considerations. Nevertheless, and because this is such a stupid context to actually discuss these things, I wouldn't do it. For image transformations, I wouldn't do that. Right? I would multiply these 3 matrices together and then apply them to all the pixels of the image. Right? So, just saying, if you are faced with the problem of turning mathematics into computer code, don't do it naively necessarily. Right? Think about what you're doing. Okay, now on to something else. We spent quite some time discussing coordinate systems. Right? Or basically, we discussed the idea of the existence of a very abstract concept we call vector spaces, and then from these vector spaces we derived ideas such as inner products and norms, and once we had norms we were able to define coordinate systems. This is not how it was done historically, but now in hindsight we could do it like this, from the abstract to the specific. What I want to point out right now is that in order to express coordinates, in particular like these simple 2-dimensional coordinates that are in the focus of our interest right now, it does not have to happen with respect to an axial coordinate system. There are other ways of thinking about expressing points. And in 2D there are not so many, but in higher dimensions there are arbitrarily many. In 2D, the case we're interested in, we can, for instance, express a point with respect to 2 axes in a coordinate system, as we have done so far. We would get the coordinates px and py. So basically we need 2 numbers to express this point, if it is a 2-dimensional point. Right? This is what makes a point 2-dimensional, that we need 2 numbers to talk about it, regardless of our perspective on this point. But 2 other numbers that would do the job equally well would be the distance of the point to the origin, let's call that one r, and the angle phi by which this line segment is rotated away from the x-axis. Of course we could do it, but conventionally it's done with respect to the x-axis. Okay? These are 2 numbers, r and phi, and px and py are 2 numbers. To compute these numbers, we typically, I don't know, start with these numbers, but that would not have to be the case. If you had a crazy camera, and well, some cameras are crazy, that would actually record images not with respect to xy coordinates, but like really with respect to r phi coordinates is equally well. It's equally okay. It's another way of talking about this point, and as long as we have fixed the origin so that we can talk about r and this, then that's okay. It's another representation of the point which does not a priori require a coordinate system. Like implicitly it does, so that we can define what this phi and r means, but does not have to be the case. And I said in higher dimensions there are many, many more ways. So this is called the polar coordinates of the point. It's a planar point. In higher dimensions we have cylindrical coordinates, spherical coordinates, whatever you want, right? They are ways of expressing points that are not tied to a Cartesian system. Yeah, r and phi are called the planar polar coordinates, and I'm just putting that planar there to really make sure we are talking about two-dimensional points here. And I said, if we are given the point in terms of its two Cartesian coordinates, say, then it is easy for us to determine the two polar coordinates of that point. Yeah, it's indeed really easy. We're given the actually let's start the other way around first. If we're given the polar coordinates r and phi, we can immediately compute the Cartesian coordinates like this. Nothing special there. It's slightly more involved to compute the polar coordinates from the Cartesian coordinates, but that can be done as well. And this is really just basic geometry. Look at this. If this looks funny to you, then try to make sense of it for yourself. Let me see. Yeah. Okay. First, now let's continue with some definition. The point for which this r is called 0, that would be this point here, right? If we are talking about a point exactly at this location, there would be no distance from the origin. This point is called the pole, and the axis from which we rotate away, or the axis for which this angle phi would be 0 degrees, is called the polar axis, and the angle phi itself is called the azimuth, typically. There are other ways, names, but let's call it the azimuth. And usually this angle phi is measured counterclockwise with respect to the axis, and I have actually shown it in this figure. Right? Now, something problematic with this equation here?
What was the question?
Yeah, pardon? There's a question?
Yeah, no. What was your question?
Oh, my question was if you would feel that this equation is dangerous? Yeah, this shouldn't be 0, right? But it can be. And this point, does exist. It looks dangerous. Looking at this, it would appear as if we cannot compute this for like all the points where px is 0. We cannot necessarily compute this, but we can the limit of this function if this approaches 0. This again something that's it looks as if there is a problem here. Mathematically there is not. We would just have to apply L'Hopital's rule to see that you can actually compute this. But again, if you were to compute this naively on a computer, you might get a division by 0. However, so you might run into a problem there. But typically, I would hope that whatever software you use does not run into this problem. Right? In particular, in order to compute this, there is this function a10(2). This is how it's called in C, and it's probably called like that in many other languages. If we want to have a look at how your computer would compute this, this is what we get. So what I do here is I just enter man a10(2) to get more information as to how my operating system, which is Linux, would compute this function a10. And it says the a10(2) and a10(2)f functions compute the principal value of the arctangent of x over y in the interval minus pi to pi radians, the sine of a10(2), blah, 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 blah. And then it tells you what it returns. And see, if x is 0, it returns something. It does not crash with division by 0. So again, this is to point out that if you are to turn mathematics into computer code and it crashes, first question yourself and then question the libraries you used. Okay, this is really, it's more likely that the error is on your part than on whatever software you have been using. Okay, before I continue, just have we seen this before in the course of our lecture so far?
Yeah.
In what context?
Complex numbers.
Exactly. Right. Remember last week we ever so briefly talked about complex numbers, and I said that a complex number is something a plus ib, where I is the imaginary unit. So a plus ib would give us something like that. And I said that in addition to this a plus ib representation, we can also think of these numbers as r times e raised to the I times phi, and that would be that. Right, so this is a geometric, or is a visualization of how we can think about complex numbers. Okay, but now something funny. This is a lecture on image processing, and we have to do lots of mathematics, and I'll show you why in a second. But let's do some image processing once in a while, all right? If we agree that points can be expressed either in, say, x-y coordinates, two-dimensional points with respect to some axes x and y, or in our phi coordinates, what would happen if we were to compute the r phi coordinate of every point in the coordinate plane we are talking about, and then plot the image with respect to its r phi coordinates? That is, we compute these two coordinates for every point, and then we define an axis called r and an axis called phi, and recreate the image. And if we follow up on this idea, what we do is we actually compute a transformation of the image, which is by no means an affine transformation. Right? So far we have talked about very simple transformations, and they are simple because, as we just saw earlier today, we can always express them in terms of matrix multiplication. We have to probably apply this trick of lifting them to a higher dimension, but those are really, really simple transformations. The idea we're discussing here is something not quite so straightforward. And I am just showing you this example, first of all, to do some image transformation once in a while, but also to point out that functions may be transformed. And so far we have looked at transformations that remain in the space over which the function is defined, but that does not have to be the case. We can transform these images into different spaces. All right? And this is what we will be doing soon later. And it plays a very important role in things that are called JPEG compression and wavelet transformations. A picture says 1,000 words. Here we are. What has happened? Here is the original image, the one we have been talking about or looking at a lot so far. And from looking at the representation I've chosen here, it appears, I didn't know, I just see it again, that it has 730 sort of pixels along the x-axis and probably 496 along the y-axis. And this is how it looks like in the xy space. And here is how it looks like in the R5 space. And now, getting back to your question, I guess it was about like if we transform something, do we transform the coordinate system, that is, do we change our point of view, or do we transform the object, that is, do something to the object? Again, looking at this, it looks like as if we have done something to this object, this function. It looks different over here. But the deep conceptual step we can make is to say these two things are exactly the same. All that has happened is that we look at it from two different points of view. And for instance, like if I look at the laptop from over here, it looks like that. If I go over here, it looks like so. I have done nothing to the laptop. I have changed my point of view, going from here to there, looking so or looking so. Yeah.
I have a point here that still in the representation of the polar system, we are looking still on the Cartesian representation, right?
Yeah, this is just because
So
I cannot visualize it otherwise.
It can't really look the same. I mean,
there is a huge difference between what your eyes can see and what an equation can see.
if we would stand on something grounded,
Yeah.
like this polar system, I guess the parallels are coming from the geography, right? So if we would stand on the polar system, which is actually it's round,
Yeah.
then it would look the same as the other one.
Yeah, but I cannot,
Yeah.
you know. This is why I say I can argue that this is exactly the same. I mean, it looks different, right? It should not. Basically, we can say this is a function g of x and y, and this is a function, let's call it h of r and phi. But g of x and y and h of r and phi are the same. Right? Cannot visualize that. And in that sense, this is really more an exercise again in accepting the fact that there is a difference between what we can see and sort of picture because our eyes are used to certain ways of seeing the world, whatever. But for a mathematical equation, it doesn't matter like how it wants to be visualized, right? And indeed, these are the same thing. They look different because I have to find some way of making it visible to us, and therefore this is how it looks like. But we can argue that this is the same. That this is just another way of looking at it. And in this example, apparently, I have chosen the pole to be this point. And of course, the polar axis was the x-axis. Right. Now, let's see if we can understand this. Where would we find this point in that image?
The point on the diagonal, the further one.
This one here, yeah, furthest diagonal is this one, upper right corner, right? Okay, you said point on the diagonal, that is, where would we find this line in this image?
Diagonal is over.
Yeah, I've heard a couple of proposals. The right one is the diagonal. Okay, let's, again, the picture said 1,000 words. Here we go. So the diagonal in this coordinate system becomes a line parallel to the r-axis in that system. Right? This is a system where we have distances along the one axis and angles along the other. So we can ask, what about all the points on this quarter circle here? So we've seen that the diagonal here becomes this line. What about the points over here?
They become square there.
They become what?
Square. Yeah.
Square. Well, what they become is another line. Right, so we have something that starts at angle 0, goes to angle 2 pi. That is to say, starts at angle 0, goes to angle pi over 2, sorry, pi over 2. Yeah, this is, you know, this is all there is to it. Why am I doing this? It's just, you know, we see some image transformations again, and we have food for thought. We can do this sort of in a more ambitious manner if we were to define the pole to be here. Right? In the previous example, the pole was down here. Now the pole is here. And if we do the exact same exercise, but with a different location of the pole, we get this. Now the angles actually range from 0 to 2 pi. Because now we can go all the way around. And the diagonal becomes a bit shorter, because now it would start here, go to here, and then to there. This is not the whole length of the diagonal anymore. And actually we see that the 4 corners of the image now become visible here in this representation. Do we need that in practice? I don't know. Later on, I guess in January, we'll see funny effects we can create with this. This is just to provoke your brains. Because we have now, we don't really have to, but I think it's a good exercise or a good idea. Given that we have discussed all this right now, let's try to get the bigger picture. What is it that we have done so far? This is not fair to ask that question, so let me answer it myself. At the very onset of our lectures, we have looked into how images are acquired. Great, right? Nothing big there. And then we looked at ways of representing images, ways of thinking about images. And we later looked at rather abstract concepts. You know, we would not have had to do it from this abstract starting point, but could argue from example to example to example and then abstract away the details. We started with a very abstract point of view, which allowed us to study more specific things such as coordinate systems, and for the last couple of lectures, the idea of coordinate transformations. And in particular, we have learned, when we learned, I don't know, it's a harsh word in this context, we talked about ways of representing images, ways of how we can conceptualize images, ways of how we can implement images on our computers. The natural thing, and again, we are focused on intensity images, the natural thing is to think about them as pixel matrices. Right? We have an image which has a certain X and Y resolution. Let's call the Y resolution M, number of rows in a matrix, and the X resolution N, number of columns in a matrix. So the natural thing to think about images is to think about them in terms of matrices. Right? And I said, well, if there is a matrix, the way the matrix is typically represented in your computer memory is as a very long one-dimensional array, where we use the rows of the matrix, for instance, or the columns, doesn't matter, rows, and put them, concatenate them one beyond the other. We actually saw that there's a one-to-one transformation from the matrix representation to the vector representation. Was there something else in addition to matrices and vectors? Tensors, yeah, right, okay. Right. In that sense, vectors, matrices are tensors, third-order tensors are tensors, yeah. But what was it? What was the concept we have been using in the last couple of lectures when talking about images? Functions? Functions, right. And really there is not much to it. It's just that instead of thinking about an image as a matrix where the individual matrix elements are certain values that indicate the intensity of a pixel, some value between 0 and 255, we can think of the image as a function that maps a spatial coordinate to an intensity value. Right? That's all there is. They are all good and well and basically practically equivalent to us. These ways of thinking about images. And then we talked about these ideas of vector spaces. And I sort of tried to convince you that there are more things out there we can think about as vectors than just these geometric vectors we are used to thinking about. In particular, I pointed out that certain real and complex valued functions can be thought of as vectors. And for the last couple of lectures, we looked into the idea of transforming vectors. Right? And on this slide, you basically have everything that we have been doing so far. Let me walk you through it again. We talked about images as matrices and vectors. Good and well, no problem there. This is the natural way of how they are represented in the memories of our computers. We said that conceptually we can think of them as functions that map certain vectors, two-dimensional vectors, coordinate vectors, to color or intensity values. Right? And then we looked at something that has nothing to do with this, but we said that certain types of functions are actually vectors. And then we looked at something that has nothing to do with this, but we said that we can transform vectors. And so far, we looked into the idea of transforming vectors when it came to vectors that were coordinate vectors. We can apply transformations to vectors, let's call them t of u, so that if we're given some function here and we do something to its coordinates, we obtain another function. And what we are going to do next is that we will get back to the idea that certain functions are vectors and that we can transform vectors. So what we've been doing up until now is transforming coordinates, and next we will actually transform functions. And the reason why I am sort of emphasizing this is that I really want you to understand what is going to happen next. And all of this was just to prepare us for what is to come, because I hope that now we all speak the same language. That if I'm talking about transformations from now on, you have some picture which you might be able to generalize to more general transformations. And if I'm talking about functions as vectors, you may have some picture which you might be able to generalize, and so on and so forth. Because what we are going to do in the next lecture is that we will get to know a somewhat very different point of view on images than the one we have had so far. And we are trying to understand this. We'll just spend quite some time. From now on, I will use the whiteboard will spend quite some time on trying to fathom what it means to assume this point of view, where this point of view comes from, and what it has to offer for us. And again, a picture says 1,000 words. Here it is. This is an image, and this is another image, but they are exactly the same. You may not believe that. But this is basically what we discussed here. This is what we see. And if we were to assume a very abstract, different perspective, we cannot physically do that. But conceptually we can. And then we can try to visualize that. And what we discussed here is that we can talk about images like in this form with respect to these coordinates, or we can talk about that if we would want to in these coordinates, and if we were to plot these coordinates somehow on a 2D plane, which is a bit of a I can create different plots of that, but if we were to plot this, then we have to accept the fact that it's not so straightforward. We have to do some practical, tricky things in order to actually visualize that. But again, conceptually, these two things are exactly the same. And getting back to that question, so we can think of having done something to this because it looks different here. But I prefer the point of view that we don't do anything to this, we just change our perspective. Again, if I'm looking at the laptop from over here, it looks different as if I were to look at it from over here. I haven't changed the laptop. I changed my perspective. And this is just another change of perspective. Well, I have to be really careful here because, you know, we're recording the lecture, so not that I get comments in the sense, oh, this is not the same, isn't it? This is indeed not exactly the same. Just as with the polar coordinates, I have to apply certain tricks to make it visible. Right? But if we accept the fact that we need these tricks to make it visible to our eyes, and that these tricks somehow make it not really exactly the same, if we abstract that away, then this is exactly the same as that. In particular, this is an image, intensity image, in XY coordinates. And what we see over here is the so-called frequency representation of the image. And indeed, to compute this here, I computed the Fourier transform of this image. And we'll discuss that in a lot of details next week, next lecture and the lectures after that. Fourier transform produces a complex valued function. But how were I to plot complex values? I cannot do that, but I can plot their magnitude. So careful, this is really not exactly the same as that. It's just the magnitude image. We saw that when we talked about these gradients, like magnitudes of vectors is basically the magnitudes of the Fourier transform. And because they are very large, like these Fourier transform image at certain pixels, I also took the logarithm to make it bigger. Apart from that, this is exactly the same. And yeah, there is pivotal turning point again at this lecture. These are all the slides I have for today. Now we can either call it quits at this point, which I guess I would prefer, or we can begin studying this. But I would possibly say let's call it quits and really start diving into that shift gear on Thursday. Is that okay? Are there any questions? Yeah.
Whatever transformations that we were discussing in the past week, we are not actually changing the data, right? It's just a change in perspective.
Yeah.
The first example that you showed us, the derivative, actually changing the
Yeah. Very good point. So his question was, I have been claiming lately, I must say, that if we apply transformations to an image, we don't change the image, we change our perspective. Now, his question was, but when we computed the derivatives of images, to, for instance, create this emboss effect, the very first example we saw, then we did something to the image and did not really change our perspective. Again, yes and no. This is a case where I would prefer the interpretation of, yes, we did something to the image. But if we really would want to, I could argue we again just changed our perspective. And this is an outrageous claim. This is an outrageous claim because I would bet obscene amounts of money on the fact that so far in your life, nobody has told you that the derivative of a function is just expressing the function in a different space. Has anybody ever told you that? No, I will tell you that in 2 weeks from now. No, it's true, it's true. It's great. So this is why I love your question at this point. Again, the example you mentioned is one where I would say, by all means, yes, let us understand this as we doing something to the image, not changing coordinates or whatever. But if we really would want to, we could also argue that we are doing something that we are changing our perspective. That, in that example, it does not make sense, but I will walk you through this when, once we have, okay, so what will happen now is, we will spend a couple of lectures on really understanding the Fourier transform, where it comes from, and what it has to offer. Right? And this is great and cool because then you can use it in practice for the applications, kind of applications it is usually used for. But I cannot leave you at that. Right? Once we have derived it from a slightly different perspective, we'll change sort of the area of attack in the next couple of lectures. But once we have done that and understood what it is and where it comes from, I will connect it all again to what we have been discussing so far. And in particular, I will point out that it is just a certain rotation. And indeed, and this is, that differentiation is just another kind of rotation. These are extremely abstract rotations, but we'll just look at it for the, just for the fun of it. Because this is a master's course, and I have to make sure that you learn deep stuff, something for the rest of your life, not just how to, implement matrix multiplication, all right? Yes, you're right. Once again, to wrap it up, let's look at that particular example as an example of when we do something to the image, but we could also understand it from another point of view. Any other questions? All right, then see you on Thursday.